Let's look at the remainder of Taylor-Maclaurin polynomials. Suppose I have a function f, and I'm approximating it with a polynomial, an nth order polynomial. Then when I do this approximation, there will be some remainder, and the polynomial plus the remainder have to equal the actual exact value of the function. Now, we're going to call the error Rn of x, and this is always going to be positive. We're always going to take the error as the absolute value, and R is going to equal f minus p, the absolute value of f minus p. So all we've done is algebraically solve this equation right here for R. Okay, so Rn is f of x minus p of x. And so this is what we're going to call our error. Now, Taylor's theorem tells us that if a function is differentiable through n plus 1 in an interval containing c, then for every x in that interval, there exists a z. Now notice it doesn't tell us how to find z, it just tells us there is a z between x and c such that f at x can be approximated with f of c plus f prime of c times x minus c. So basically the expansion to the nth term, so this is my nth order polynomial Taylor approximation, plus the remainder. And here's the beauty of this one. The remainder is equal to the next term. The remainder is the n plus first derivative evaluated at some point z in there times x minus c to the n plus 1 divided by n plus 1 factorial. Now here's the trick. We have to usually find the bound of the n plus 1 evaluated at z. We don't have to find exactly what z is. All we have to do is usually find this as some bound. Let me call this b, all right? So this is the trick to these problems, is computing this remainder. And the remainder, you remember, is just the next term of the Taylor polynomial. So let's look at a Maclaurin polynomial for sine of x. And we're telling you that the Maclaurin polynomial is x minus x cubed over 3 factorial. Now, I want to use Taylor's theorem to approximate sine of 0.01 by p of 0.01 and find the accuracy of my polynomial. Now, according to Taylor's theorem, sine of x is equal to p3 of x plus the remainder of 3 at x. So p3 of x is x minus x cubed over 3 factorial plus, now you remember the remainder, this is a 3, so it's going to be the fourth derivative evaluated at some point z times x to the fourth, because it's Maclaurin, divided by 4 factorial. Now, let's look at what z can be. Z, we can see, has to be between, it's not even less than or equal, it's just less than 0.1. So z itself is bounded. So I can make the approximation sine of 0.1 is approximately equal to my polynomial, 0.1 minus 0.1 cubed, divided by 3 factorial, or about, now you do have to use a calculator for this, 0.099833. So I've been able to use the Maclaurin polynomial to approximate sine of 0.1. But I want more than just the sine of 0.1. I want to know what is the remainder. So let me switch pen colors here. So f to the fourth of z is, if I do the derivatives here, let me go back up. If I do the derivatives of f, if f of x is sine of x, f prime of x, derivative of sine is cosine of x, f double prime of x is minus sine of x. So f 1, 2, third of x, I lost count there, is derivative sine is cosine of x. All right, so the fourth derivative of x is plus sine of x. Okay, so because I know my fourth derivative, evaluated as z, is sine of z. Now, what do I know about sine of z? I know sine of z is bounded by 1. All right, so I know sine of z has got to be less or equal to 1. And remember, we're doing absolute values. So let me look at my remainder. The remainder, all right, is equal to, and I'm just going to rewrite this, because I lost it up there. All right, so what is R3 at 0.1? Well, it's some sine of z, and I don't know what that is, and I don't need to know what that is, times 0.1 to the fourth divided by 4 factorial. And I know this has got to be less than, it's going to be greater than 0, and less than, sine is bounded by 1, so it's got to be less than 0.1 to the fourth, or 4 factorial. So I know my error has got to be less than, and this is going to be really, really small, 0.1234, 4 zeros here. So that gives me a bound on the error. So I know sine of 0.1 is 0.0099833. So sine of 0.1 is approximately 0.0998833, and that is going to be plus or minus 0.00004. How many zeros do I have? 1, 2, 3, 4, 5 zeros. All right, so I know the sine of 0.1 has got to be less than 0.099837 and greater than 0.09983.